Alrighty, everybody. Recently, there have been some changes to read CSV that I want to go over, show you how to use it. Right now, this is going to be a primarily Groovy focused example, but Jianfeng has the task of making it prettier and even easier to use from Python than from Java or Groovy. So I'm going to go ahead and present my screen here.
Yeah, and Jianfeng, the target's about a week from now, correct? He's either not there or muted.
Sorry. Yes. Yeah.
Is everybody able to see my screen?
Yep.
So we're just going to go ahead and dive
A little
right in.
small. Can you zoom in?
Let's see. Let's see. There we go. Tell me when.
You're good.
Okay, there we go. So I've got a bunch of examples here. Basically, you're just going to walk through them. I'm going to talk about them a little bit. Feel free to stop me at any point and ask questions, or we can ask questions at the end. So we have a package called CSV helpers, and that's where all the new functionality has gone. The existing methods that are in table tools are re-implemented to point to the CSV helpers. I think eventually, if we're not already, these will be imported by default, but right now they aren't. So right now I'm just gonna load up a sample CSV file from the Pirate Bay from a specific date in 2008. And then just do some simple statistics on it. This is hopefully a pretty simple thing to do. So we'll just pull in the CSV file here to see that you can see that it went ahead and read it. So there's 5 columns here, a torrent ID, the category, the file size, and the number of seeders and leechers. Very simple, read it, and it figured out this is an integer, this is a short, this is a long, and these two are integers. We'll just go ahead and do some simple statistics on it so you can see it is a real table and we can do real stuff with it. So you can see here the averages for that file, here are the different categories, and then here are, let's say, the outliers, the biggest seeders and leechers for that specific day. So there's some file that was really popular and had over 50,000 seeders and leechers. So that's just a simple example to pull from the CSV. And this is reading from disk again, so that's what we're demonstrating here. We'll do another one from disk. This is a crypto trades file that Pete has generated. I haven't done any analysis against it, but we'll go ahead and just run it. And we'll see that it pulls up a different CSV here. Crypto trades, string. Here we've got a DB date column. It's got a long ID, some rows, or instruments and a million rows. An exchange, double price, double size. Pretty simple. So.
And just noting that timestamp was a long on the CSV, so it did.
Yeah, we'll see that later, Pete.
Shoot, sorry.
Later on in this example. He's jumping the gun here, but that's okay. So let's go to. So let's say that this was not enough, and we wanted to provide some more. Some information so we could choose our column types. That's where the custom header comes in. So using the QST column types, we can go ahead and create a table header here. Date, timestamp ID, instrument, exchange price, and size. So the changes I'm going to make here from the previous one is, let's just say that ID is a string instead of a long, and we've got a instead of price and size being doubles, let's say we wanted to save a little bit of memory and make them floats instead. So we can basically do this map here, and we can pass it along to the CSV specifications and then pass that in to read CSV. So we'll go ahead and run this. And we'll notice here our ID here is a string instead. and then our price and double or price and size are floats instead of doubles. So one of the overall goals here is to try and reduce the amount of method overloads that we have to deal with from the Java and Groovy side of things. So instead of having a dozen or 2 dozen or 3 dozen read CSV methods, potentially with different names, what we're trying to do is we're trying to encapsulate all the different options that we might want to set via this CSV specifications object. So we can use this builder pattern, and there's a bunch of different options that we'll see we can tweak, and then we've essentially got one method that we're targeting here to get our end results. This may be a little bit verbose, and it's kind of just the nature of Java and in Groovy, at least right now. I'm hoping to motivate people that it's going to be really cool when it's in Python, because we'll be able to have some custom wrappers around it, and we'll be able to do something that looks like this, where instead of using the builder pattern for the headers in Python, we'll be able to use a dictionary, mapping the column name to the type. And so this is what it will look like, or what it might look like in Python coming soon. So that's something to look forward to, I think. One of the new things is we've got a new way to invoke this, and this is via URL. So if we wanted to load some Seattle weather data, we can go ahead and wrap it up in a URL object. And we hopefully this URL is working right now. Go ahead and load it up. And there we go. We've got some data that we've loaded up from a URL. Go ahead and sort by temperature if we wanted. Maybe I shouldn't have done that. There we go. So that was a particularly cold day, it looks like, in 1950. One of the things we're trying to do, though, even from the Groovy side, is to be a little bit more user-friendly, and wrapping this up in a specific URL object, while very specific, is a little bit less user-friendly. So what we're going to do is exactly the same thing, but instead of the URL wrapper, we can just use a plain string. So when you use a plain string here, it'll be able to notice the difference between the file path and then a URL. So the same example right here, we can run it, and hey, there we go. We got the same exact output. So you don't need to remember to use this URL unless you want to be very specific about it. Otherwise, you can just use a string and point at a URL or a file path, and it should just work. And next thing we're going to go here is headerless. So we've got a headerless example on our examples repo, Deniro headerless.csv. To aid in the builder pattern for a couple of common CSV specs, there are some pre-built definitions here. So there is a pre-built headerless definition right here. So you don't have to do the builder pattern. You can just say you want headerless and then pass that in. And so this will parse this in the headerless fashion. When there aren't any headers, the column names by default are column 1 through column n. We got a short here, we got a short here, and we got a string here. And then
does the builder also have a headerless?
Yes, the builder does have a headerless, and that's a good question. I'll demonstrate that right here after this. And then, of course, if you want to rename the columns, you can apply a view on it afterwards and title the columns whatever you want. If you wanted to do this via the builder pattern, what you could do, we'll just comment this out right here. I'll show that it's exactly the same thing. Builder has header row false build. So this is just a shortcut for this. So I'll go ahead and run these two things. And there we go. So that's the builder pattern for that. Good question. Of course, if you're reading stuff in headerless mode, I think it's a very common use case to want to be able to specify what the actual header is. So one of the pre-built or one of the static methods on CSV specs is to provide a header as well, because I think that's going to be a very common thing to do. So you can specify your header. And again, once we're in Python, this could be, a very nicely typed dictionary instead. So you can say headerless, but I want to use this header. I want to read that CSV and use these specs right here. So if we execute all this right here, there we go. And it's got our int year, our byte score, and our string title. I chose to use a byte here for score because it's, I think, between 0 and 100. So we don't need to use a short or int. We can use a byte just fine. And if you wanted to do this as the builder pattern, what you would be able to do, so we'll just do builder.has header row false dot header dot build. So that's how you'd specify both of that like that. So in that case, if we execute these two things, it's the same end result. There's another pre-built default for tab separated values, just called .tsv. So just like .headerless. This one does have a header, but it's using the tab character separator on the TSV file. So we can go ahead and run all of this. And there we go. Not too exciting to look at right here because the output is the same, but the input is a little bit different. If you wanted to do this one manually, limiter, go tab as character. So that's how you do that one. So run all of this. Where did you? Yep. So in Groovy. Okay.
Beginning of line 5.
Oops. Yeah. Okay. Yeah. So we weren't actually using that. There we go. So let's make sure we actually are using it this time. Run these. And there we go. So output's still the same with this built this way. Now let's say you want to use a custom delimiter. I've kind of already given away what that's going to look like. But what we'll do here is there's a file that I found on the internet that uses space as a delimiter. It's actually from the Twitch leaks that happened last week. So a timely kind of news story here. We're going to drop the username and user IDs. Don't want to show that, but we'll just look at some gross earnings from Twitch. Go ahead and run these custom stuff right here. So here is, I think it's a couple years worth of earnings data from Twitch. And we'll just go ahead and plot it right here just to see a fun graph.
So I see in your examples here, the delimiters are characters. Can we handle multiple character delimiters, so string delimiters, or not?
Not at this point in time. It's possible that we can do that in the future, but the interface right now is specifically characters. If we find a CSV file where we need that or people are asking for that, this can be changed in the future. If we wanted to, so this is a very top-heavy graph. Let's say we just wanted to see somewhere more around the median, so we could say where rank was greater than that. We could run this again. We could look at kind of the tail of this graph right here. So there's, the 5,000th to the 10,000th earnings for this graph right here. Let's go ahead and close those. Now let's get into inference. So when we're parsing a CSV file by nature is all plain string data. And so we have to have some way to be able to parse the different columns and figure out what types we want. And by default, we parse a lot of different types. This is what we parse by default. It's what we're calling standard times. This is just a name for a long list of parsers. So we parse the ISO 8601 instant spec. Then we've got a DB time legacy spec that we try to parse. And then you can parse along as seconds from the epoch, and then or as millis, or as micros, or as nanos. And then you can try to parse it as a short, or as an int, or as a long double bool char string. So this is the standard inference order that we use by default. And again, that's called standard times. I'll go ahead and run this right here, and you'll see this is going to be the same crypto trades that we saw earlier with the standard inference. So we've seen this file before. Parses timestamp as a DB date time. Let's say we wanted to parse everything as strings instead. So instead of
is it parsing the long as a time because of the column name, or for some other reason?
No, it's parsing it based on looking at the data. So I'll get into this a little bit more right now because I think it's generally useful to know. But these are ordered in such a way that it's none of these formats are supersets of anything that comes after it. So, for example, if on this format integer came before short, we'd never parse a short because anything that's a short is also an int. So it's kind of laid out in the most specific way to least specific way possible. So first it tries to parse a column string as ISO 8601 instant format, which is what the standard Java instant parse is. Then we've got some DB. If that fails to parse, then it'll try to parse it as a legacy timestamp, which has some other logic behind it. And then these other ones it will try to parse it as if it were second since the epoch, but it limits it to the range of the 21st century. So if it's in the 21st century and it looks like seconds, it'll pass this parse filter. And then otherwise it'll try millis, micros, short, long, double, and it'll have to pass through the whole column before it can figure out what type it is. And if we ever fail parsing for any cell, then we don't have to try to infer that type for that column anymore. It's getting a little bit into the implementation details, but hopefully you can see that we're trying a lot of different parsers here for each of the columns. So let's say we didn't care about parsing the column types as anything but strings. We could say we just want to parse the strings. We could create these CSV specs, and then we could read these trades in as strings. And so this, basically doesn't do any inference. Everything is a string. Date is a string here. Timestamp is a string here. ID is a string here. And so this is basically the raw values from the CSV file. So if you ever need to debug a CSV file because the parsing isn't quite working, or you're not sure why something's looking that, obviously you can open up the CSV file itself and go through it, but you could also try it with the strings inference and get everything the strings.
So in this inference, in this ordering, I can imagine that this could be time consuming, if your last value is the one that's different.
Yep.
How are you approaching that to have reasonable efficiency on bigger files?
There's a couple things you could do. You can be very, if you know your types beforehand, obviously specifying your header up front is going to save time on inference. That's a good point, though, that just specifying the type of the column isn't always a one-to-one mapping onto the actual parser that's going to be used, because as I've shown here, if you specify a timestamp, well, we have 1, 2, 3, 4, 5, 6 different ways to potentially parse a timestamp. And so if you specify a column as a timestamp column, it's going to do inference just on those 6. And the hope is that it's going to be selective enough that only one of them will ever pass. They're tried to be built so they're non-overlapping, and by limiting to the 21st century, at least by default, the seconds will never overlap with the millis, will never overlap with the micros, will never overlap with the nanos. So the hope is that once you parse the first column, you're able to eliminate a lot of these right off the bat. So we've parsed this as a string now. And this is the point that Pete brought up earlier, that this column actually looks an awfully lot like a long, and I'm not sure if it's nanos or micros or millis. Maybe it's nanos off the bat. I can't tell. Looks like it might be nanos. I don't know. But you'll notice when we do use the full inference, the full default inference here, and run it, these timestamps as longs do get correctly interpreted as DB date times. Right. So there we go, DB date time. Some other pre-built specs or inference specs that we provide that I've built up. And there is potential for us to build more if we find like there are very common use cases where we want to have a different inference order. We can definitely add that. So here's an inference order where it just tries to part as an instant, as a long, or as a double. So we'll go ahead and set that as the inference specs. I'm calling this a minimal spec because it's not doing much. Actually, I think there's string. String is the last one here. Go ahead and parse minimally. So in this case, we've got a string, we've got a long string, and then doubles over here. The other inference spec that we have is one that is kind of all the standard types. I'm leaving byte and float out of here, and the special timestamp parsing ones that you could use right there. So that's the order right there. And then just our standard one that we've seen here before. So there's a lot of potential ways to tweak how inference works if we are so inclined to do that. I'm going to go over the builder object here a little bit more. So here are all the defaults. So it has inference of standard times, has a header row true, has a comma as the delimiter, has the quote character as a quote character. These I'll just describe. I don't have any examples that I want to show specifically with them, but ignore surrounding spaces is true by default, and trim is false by default. And so what this means is when you've got a CSV file, I'm just typing it inline here, so bear with me here. When you parse a file like this, ABC, let's say that's the header and these are the values. When you say ignore surrounding spaces, and this is the default, it's going to trim any white space out by default before or after the value, right? So this is going to be interpreted, or it's going to be parsable as a numeric type. And this is going to be parsed as a string without the space character.
So how is that different than trim?
Yep. And so ignore surrounding spaces is outside of the quote characters. So it trims outside of the quote characters. So since we don't have any quote characters here, it trims everything. Now, so trims inside quote characters. So if we had this instead, it would not trim these values by default because they have specific quote characters that have specific spaces inside of them. Now, if you wanted to trim inside of quote characters, that's where trim comes in. And you go trim true, and then that would parse this string and trim this character out and trim this character out. So most of the time what I've seen is you want to trim extra space as long as there aren't quote characters that are specifically there. And if for some reason you didn't want to trim this and you wanted these spaces in here, you could set this to false right there. If we want to provide better names for these, we can. There is some Java doc on here that says it is out, trims outside of the quote characters and this trims inside. But I've tried to provide what I think are the most reasonable defaults here of trim outside of the quote characters, but don't trim inside by default. And then one of the other things I haven't demonstrated now, and I didn't want to get into it for this example, but is you can specify custom parsers for your column names. So if you have some fancy data that you want to parse differently than the standard double or standard integer or timestamp stuff, there is a class you can extend that's a parser class, and you can put it into your CSV specs right here. So you can say, I want this specific column to use this specific parser. And of course, you could combine it with these other options if you wanted to, but that would allow you to fully customize what the parsing logic for that column is.
Okay, so you are assigning a column name to a parser. Can you throw that into the inference as well or not?
You could add your custom parser as a new inference. What that's going to look like is you'd have your inference specs .builder. Let me make sure I have the syntax here correct. So I'll give an example here of our standard. It's going to be builder.add parsers. You would be able to reference parser. You could say like .int, parser, .long, and parser, or it would be, my custom parser. So you could have that as your inference spec if you wanted to. You're usually going to end your inference specs with a string because otherwise you default back to string. But that's how you do a custom inference spec. I'm not going over right now how to create my custom parser because that's going to be more advanced interface with specific parsing logic. But that's how you would add it to the inference as opposed to a specific column name.
Okay, and then as far as the parsers go, do those need to be in a JVM language, or is there a way to do it in Python reasonably?
There's probably a way to do it in Python reasonably. I think that is out of scope for the first pass at the Python parser.
Yep.
Or this for the Python CSV integration. I'm sure there would be a nice way to be able to do it in Python, but I don't know how often something like this would be used. But it is possible. So. And then the one other thing actually that I might be able to go over, I didn't have time to already go over it, but we can parse zipped and compressed files by default as well. Give me 1 second here. Here we go. Here's an example. Let me create a new file here. Oops. call this 12. Oops. So I've got a file right here compressed with the Z standard compression, which is going to be something like zip or gzip, but it's a pretty performant compression. So what we can do is we can go x equals text. This is a decently sized file. Go ahead and of course, when I try to do something, I want CSV helpers, not CSV specs. Sorry about that. We've already got it imported, so we'll just run it here. And what we support here is Z standard compression, B zip compression, G zip compression, zip compression, and BZ2 compression, as well as all those formats potentially tarred up. So here is the example file right here.
Quick question.
Load it up.
When you say you support compressed files, that's a compressed CSV file, right?
Correct.
Okay, so not like a zip of multiple CSVs or some other weird structure.
So that's a good question. There is a slight difference in terminology when you say there's a file that's compressed versus there's a compressed archive.
Gotcha.
And a zip file is actually an archive format, not a file compression format. But what we typically do is just assume it's the first file in the archive. So all zips are archives, and we just take the first file out of there. So here's the zip version of it. I'll go ahead and run this.
Yeah, I mean, it may be safer to have an exception if there's more than one file inside.
Yeah, that's something we can do too. Historically, we haven't done that, and we've just taken the first thing in the archive. But that's something that could easily be changed, I think.
Got you. Sounds good.
Just curious, let's see what the difference in times were for those commands. So our Z standard was 16 seconds and our zip was 22 seconds. So, we are about 25% faster reading from the Z standard version. And it's about 2 million rows or so with 6 columns or so.
It could be nice if you have multiple zipped CSV files in the archive, and we just return, a list of tables.
That's an interesting idea. That's more of a, you're taking your entries from your zip or from your tar, and you're reading that as the table. I think that's interesting. That's not related to CSV parsing at all. But I think that could be a useful other utility if people want to explore file types or something like that. So
I just want to confirm my understanding. So I guess with this, I expect everything to be read in as an in-memory table. Is that true, or are there any exceptions?
Yep. These are all being read in as in-memory tables. These aren't like binary formats like Parquet files. I could demo reading in Parquet files, but I think it's out of scope for now. So yeah, all these are brought into memory. You need to make sure that you have enough heap to reasonably deal with the size of your file. We are trying to be smart about how we parse things in the order that we parse things and how we infer stuff. But at the end of the day, if you're bringing a whole bunch of strings into Java, there is going to be some amount of memory overhead
And
with that.
and do you have any like guidelines on that? Is it 25% more, 4x as much?
I don't have any good guidelines on that. I would say at least twice as much. And maybe that is an underestimate. I've got an even larger file here. I think I'm running with my standard 4 gigabyte heap here. Let me double check. And we'll try to load a big file. Maybe we're going to blow up and maybe not. Yeah, so
Yeah,
I've got
I'm
4
noticing a potential memory hogging issue in read CSV.
So let's get a big file here. Let me just preface, figure out what the size of this file is. So this is a gigabyte file about.
Oof.
So I've got a 4 gigabyte heap. I'm pretty sure I've run this before, but nothing can go wrong during a demo. So I think we're good here. I'm going to go ahead and just null it out first to make sure we have some space in case we need. Still got a bunch of tables open. That's okay. Well, let's see what happens here. Again, so this is a gigabyte file. I don't remember. It's about
Can you
7 million
can you
rows.
run Docker stat and just monitor it?
I mean, I can run it myself. You're not going to be able to see
Yeah,
it 'cause
yeah,
I'm not
sure.
sharing that. That's it at the screen. Looks like we are pretty close to our limit here. We'll see if our JVM crashes or not. And we
Cool.
crashed. So, yep,
Oh,
we crashed. Let's go ahead and refresh this here in a second.
What's the crash message? Is it GC? I forgot the.
It might have been Docker might have hard killed it. I'm not sure in this case.
Okay.
Sorry, having some Docker issues here.
I hope all the examples you just did are saved and can share with us.
Yeah, I've got all this. Well, I think I've made something unhappy, so I'll leave it at that. Sorry, I dropped you out there for a second. Internet's not the best here. We delegate to the Apache Commons CSV Parser, which I don't think is particularly multi-threaded. We don't try to do anything special to be multi-threaded. It is something we could add for sure if we wanted to on our end, kind of do the columns in parallel. There is some potential to replace the underlying parser with a streaming tokenizing CSV parser. I think at the end of the day, that would be very helpful for, at the very least, memory consumption. It may end up being a lot faster as well, but that is another CSV project that we'd need to undertake if we wanted to try to make it faster like that. So.
Okay, and is it, if we have a user that is like very concerned about this, how hard is it to switch that parser out? Is it very tightly integrated, or is it loose enough where it's not a major project?
I'd say it's it depends. I think our top level interfaces would stay pretty much the same. It would be probably at least a week-long project, I'd say, to try to switch that out. So,
okay.
At the end of the day, though, you are bringing the table into memory. So, I mean, I think CSVs in general are good for ad hoc data ingestion, public data sets. If you're really concerned about general performance or specific performance for a specific very large file, we can point users to translating the CSV files to Parquet files or other binary formats that would not bring stuff into memory.
Yeah.
The biggest ones I've seen have been like 2 gigs or something, and we can make the heap probably manage those.
Yeah.
And if it's
like
more
I
than
said,
2 gigs, yeah, they're doing something wrong.
This 1 gigabyte file, I have loaded it, but I think based on all the other example data that I did.
Well, and 4 is not a very high to have your heap at right now.
Yeah.
Yeah, I mean, I think there are 2 dimensions here. One is the memory usage, and the other is just the load times. And I know that in Python and Julia, they publish the load times for CSVs because some people really care, and some of those are some of those libraries are very, very multi-threaded.
You mentioned zip archives as well as pulling data from a URL. Apologize if I missed it. Can you pull a zip archive from a URL?
That is not something you can do right now. It is something we could definitely add. One of the things that we did previously that is different than what we do now is we inferred the archive type based on the bits in the file. And I wasn't very happy with that. So what I'm doing now is I'm inferring it based on the file extension instead of trying to read some magic bytes from a file. So if your file ends in .zip or .tar.zip or .bz2 and you're reading from the file system, it will automatically apply the decompression logic for that based off of the file extension. It's a little bit different when you're trying to open a URL because there might be query parameters or there might be other parameters in the URL, or when you query a server, I believe there's another part of the headers that are returned, like the file name can be returned as part of the HTTP headers. And so it's a lot less clear to me how to automatically apply decompression when you're loading from a URL in a consistent way. Maybe you can say, if this URL contains the string .zip, then automatically apply zip decompression, but that's a little bit further than I wanted to take it right now.
Yeah, I mean, couldn't we have a thing similar to the inference that just checks the format?
I worry.
It's better to have it at the read CSV level, and it's going to be a little bit nicer from Python 2, I think. We can say from the Python side, it'll be very easy to specify, load from URL and use zip decompression or something like that. And we could add those on the. I don't think it belongs in the CSV logic side of things, but I could see it on the read CSV method, adding the file type or any decompression logic. I mean, again, one of the things we're trying to do is trying to minimize the amount of method overloads, and so maybe in that sense it does belong in the CSV specs, but it doesn't exist there yet. So
I don't.
We could add a compression hint parameter to the Python API, I guess. Okay. Go ahead.
I don't think we should encourage users to use zip files unless they can visually inspect them. And so downloading a zipped archive of CSV files or something, I think, is probably not a good practice we should encourage.
Yeah, I mean,
I would take the opposite side of that, just because everybody does it anyway.
yeah, I mean, I'm fine trying to add some sort of logic onto the URL stuff to automatically decompress it. It just hasn't
No,
been
I
done
would
yet.
make it explicit. At least from some point, perspective.
I mean, like we
You
could
tell me
do we
what
could do
what
exactly the
type.
same thing that we do in the file path case. If it ends in .zip, if the query part ends in .zip, then we'll assume it's a zip file. And I think
Right.
that's it's a reasonable thing to do. Of course, when the user, I mean, this is the same on the file case as it is in the URL case. Like, if the user provides a file name that ends in .zip, but it's not a zip file, then our current code is not going to handle it well, right? So there's that case too. So
I see.
and again, the hope is that Jianfeng's able to take kind of this builder structure that has been created due to necessity to minimize overloads in Java and to make it pretty to use as named parameters in Python. And that's kind of my common theme when I'm gonna, potentially in the future, when there are other APIs that I'm looking at, trying to minimize the number of overloads and providing some sort of specification builder for options behind that. And then in some sense, you can think about all these builder options on the Java side are probably going to correlate to named parameters on the Python side. So whereas on the CSV specs, I have to do, CSV specs.builder.header, then I give the header object .has header row true, delimiter, then I give the delimiter character. Like on the Python read CSV side of things, is going to be, header equals your dictionary, has header row equals true, delimiter equals whatever. So you're going to get rid of the builder abstraction probably from the Python side of things.
Sure. So that's basically our wrapping strategy for, at least CSV, if not for anything.
I mean, I think it's going to, at the end of the day, it's impossible to satisfy every single use case of every single user might throw at us. I mean, if you look at I believe it's the Pandas read CSV code.
Oh, that is disaster. That's so many parameters.
I mean, there's I'll paste this to the channel right now. It's not that I want to be too critical of it, because there may be a point in time where we need to provide 100 different configuration options, but it looks like there's
2 dozens. Last time I counted.
Yeah, like at least 3 dozen, at least 30 different
Oh,
options
3
I can give here. And they might all have their use case. They might not. I'm hoping that we can expand our configuration objects or configurationable parameters kind of organically as necessary. I don't want to try to just provide everything right out the gate without some real use cases behind it. So, I'm happy to provide more configuration options as real use cases arise. But I think what we've got now, it's handled all the cases I've thrown at it. I mean, JJ points out a good example. Compression from a URL, that may be the next feature that we want to add to it, because it doesn't exist right now. But yeah, there's.
So, Devin, where can we find all the examples you just did?
You can rewatch the video. No, I'll post them. I may not upload all the data, but obviously anything that's via a URL hopefully will still be there. I mean, that's the other thing.
They could be put in the example repo though.
They could,
These
yeah.
are good
I
examples,
don't want to put the Twitch leak data in our repo. I thought it was just a fun example that I already had that I tried locally. You know, there's a convenience factor using URLs. There's also a risk of link rot and stuff not working in the future. So whenever we create examples, canonical examples from URLs, it's best if we own the URLs and can keep that data working. Like when you point to a random URL with a random CSV, that might not exist in the future, or the server might be down, or the internet might be down. So there's potentially a lot of caveats when trying to make canonical examples with URLs, but I won't argue that it is very convenient. And when things are working, it is a good option to quickly share snippets with other people.